Hey guys, this is Miss Clark with 10.4. We're going to be talking about areas of regular polygons and composite figures. So before we get started with actually looking at some area formulas, we're just going to talk about some terminology that is going to be used consistently throughout this video. So first we'll say that the center and radius of a regular polygon is also the center and radius of its circumscribed circle. So what that means is just that the shape is fitting exactly inside of the circle where all of my vertices are touching the edges. It's not a super great diagram because it's not exactly perfectly fitting. But in an ideal world, if we had a perfectly regular polygon and we were to set it in a circle, each corner of our shape would touch the circle at exactly one point or whatever. So it says the center of our circle is the same as the center of our shape. So in this case, the center here would be P. And then it says the radius is also the radius of the circle. So we can see that the radius of my pentagon is going from the center to the edge of the circle. And it's also in our shape going from the center to one of the vertices of my shape. And that's going to always be true. So PA would be a radius of my shape and PB would also be a radius of my shape. So just going from the center to basically one of my corners. So we say PA is a radius and PB is a radius. Okay, so now we're going to introduce a term that we might not have heard before, and that is the term apothem. And an apothem is a segment drawn perpendicular to a side of a regular polygon. So what does that mean? Well, that means the apothem is going to go from our center and it's going to go straight towards one of the other sides. And as my apothem does this, it's going to do quite a few things. So I'm going to go ahead and draw another radius here, just so we can really see what's happening. So my apothem is going to be perpendicular to one of my sides, and it's going to cut it exactly in half. Because I have a regular polygon, it's going to be perfectly symmetrical, and all of my sides are the same. Not only is it going to cut my side in half or bisect my side, but it's also going to cut this angle in half. And this angle that's kind of created by two of my radiuses coming together towards the center is what we call a central angle. And so a central angle has its vertex at the center of the polygon, and it passes through consecutive vertices of the polygon. So it's always going to be right in between two vertices. So CPB would be an example of a central angle, and also APB would be an example of a central angle. Okay, and then how we find the measure of our central angle is that we can take this circle and use the fact that our regular polygon is circumscribed inside the circle to find the measure of our angle. So basically, we know that a circle is 360 degrees, right? And if I were to draw all of my radii into this shape, it would cut my hexagon exactly into 5 congruent sections. So in order to find one of my central angles, I'm going to take my whole 360 degrees and I'm going to divide it by 5, or 1/5 of the whole circle, since that's going to be just one of my central angles. So in the example of pentagon ABCDE, my central angle, or we could say maybe angle APB, would be equal to 360 degrees divided by my number of central angles, which is 5. And here that's going to be 72 degrees. And in general, if we want to find the measure of a central angle, we can take 360 degrees and we can divide it by our number of sides, where n is equal to my number of sides. All right, so we can find our central angle, and our apothem is going to cut that central angle exactly in half. And then it's also important to note that our radius that comes down towards our vertice is also going to cut this vertice exactly in half, or it's going to bisect that. So there's a lot going on here. As we continue to sort of go through a few examples, we'll get a little bit more comfortable with the terminology. But let's go ahead and attempt one of the area problems now that we know a few more of these pieces. Okay, so example 1 says, what is the area of a regular hexagon with side lengths 10 inches? Give both the exact answer and the approximate answer rounded to 2 decimal places. All right, so what I'm going to do here is I'm going to sort of scoot in on my hexagon so we can get a nice good look at it. And then I'm going to label it with what I know. So I know that each side is worth 10. I'm going to go ahead and label everything 10 except for that bottom side. And we'll see why, because that's where I'm going to kind of draw all of my stuff happening. Okay, so and then based on what we just talked about, I'm going to draw a center, try and make it right in the center as I can, and then from that I'm going to draw 2 radii, and then in between my 2 radii I am going to drop my apothem. Now because we know the apothem is going to bisect one of my sides, then that means these 2 pieces down here are going to be 5 and 5. And our goal here is going to be to find the height of my apothem, because what I want to do is I want to find the area of this triangle. And I know that the area of the triangle is 1/2 base times my height. And I know my base is 10 because that's the side of my hexagon, but I don't know the height of my triangle because that's my apothem. If I can find the area of this triangle, then because I know that my radii basically cut this exactly into 6 congruent triangles, I can just take what the area is of this bottom triangle and multiply it times 6, since each one of these is going to have the same area. So in order for me to find my apothem, I'm going to need some more information. And well, I know from what we just talked about that I can find the central angle of a polygon. All right, so the central angle of my polygon is going to be 360 degrees divided by my number of sides, so divided by 6. So that means my central angle is going to be 60 degrees. So each one of these is going to be 60 degrees. Now, because my apothem is going to split that central angle exactly in half, what that means is each one of these little angles in here is going to be 30 degrees. Now, from this point, we might see that we have a 30, 60, 90 triangle because I've got a right triangle and one of my corners is 30. So by default, that must mean that my other angles down here are 60 degrees. But just to kind of prove to ourselves that this is in fact true and we did the math correctly, I'm going to go one step further and I'm going to find the measure of one of my vertices using one of the formulas we talked about in a previous section, where I do n minus 2 times 180 and then I divide by my number of sides. So since I have 6 sides, I'm going to do 4 times 180 divided by 6. And sure enough, when I plug that into a calculator, I get that this angle is 120 degrees, which makes perfect sense because my central, or my radius, is going to cut this vertice exactly in half and create 2 60-degree angles. Now, when we go through problems like this in the future, it is your choice whether you want to find this angle here first or this angle. So whether you want to find the central angle or you want to find one of your vertices is up to you. I would argue that the central angle is a little bit easier, but for some reason I'm a weirdo and I like to find the vertices of my polygon. So either way is fine. It's just going to change how we set up some of the problems, but we'll still get to the same answer no matter what because of the properties of a right triangle. All right, so now that I know that I have a 30, 60, 90 triangle, then I also know that across from my 30 is base length of 1, across from 60 is root 3, and my hypotenuse, or across from 90, is 2. So I'm going from a base length of 1 to 5, which is going to mean I have a scale factor of 5 here. So if I want to find my apothem, I'm going to multiply 5 times root 3. So x is equal to the square root of 5 times the square root of 3. All right, we have our base and we have our apothem, so now we have enough information to find the area of our one triangle, and we can use that to find the area of our whole hexagon. So kind of scooching back out here, back to our problem. If I want to find the area of my hexagon, let me make that pen a little bit thicker. If I want to find the area of my hexagon, I'm going to take the area of one of my triangles. So the area of my triangle is 1/2 base times height, so it's going to be 1/2 my base, which is the side of my shape, so that's going to be 10, times my height of my triangle, which is my apothem, which is 5 root 3, times 6, because I have a 6-sided shape, so I have 6 different triangles in there that are all the same. So multiplying this out, I have 1/2 of 10 is 5, times 5 is 25, times 6 is 150. Square root 3 inches squared. And then if I want to find the approximate answer, I could plug that into a calculator and do 150 times the square root of 3 and get about 259.81 inches squared. All right, so how can we use this information to construct a general formula for a regular polygon shape? Okay, so the area of any regular polygon is going to be the area of a triangle, so 1/2 base times height, where my base is the side of my polygon and my height is my apothem. And then we're going to take that area of our triangle and we're going to multiply it by however many triangles we have in our shape, which is going to be the number of sides in our shape. So 1/2 SAN, where S equals our side, A equals our apothem, and N is equal to the number of sides. Now it's important to note that if we were to take the number of sides and multiply it by our side length, that would give us our perimeter. So for example, in example 1, if I have side lengths of 10 and I have 6 sides, then that means my perimeter is 60. So instead of doing SAN, I could also say that my area of my polygon is equal to 1/2 my perimeter of my shape times my apothem. And we can see that's true in this case. If I were to take 1/2 my perimeter of 60, times my apothem of 5 root 3, then I get 1/2 of 300 root 3, which is 150 root 3. And it is in fact the same thing. Now, while this is a simpler formula to memorize, I find that I like to use the first one better just because it's not something I have to memorize. It's just intuitive to me that I'm finding the area of a triangle and then I'm multiplying it by the number of sides. But feel free to use either one of these formulas, whatever is most comfortable to you. All right, now that we have done one example, I want you to go ahead and attempt to do example 3, 4, and 5 on your own. So I'm just going to kind of zoom in on these for a second and scroll down so that you can pause the video and attempt each one of these. All right, so go ahead and pause, and then we'll come back and talk about the solutions together. All right, so let's go ahead and go through these. So in example 2, I constructed my hexagonal shape, and because I had a perimeter of 30, I knew that means that each of my side lengths is going to be equal to 5. Now, because it's asking for an exact answer, rather than break these two side lengths into 2.5 and 2.5, I wrote them down as fractions because I don't want any decimals in an exact answer. Okay, so just like last time, because I have a hexagonal shape, I know that my central angle is 60, so I'm going to have two 30-degree angles up here and then two 60-degree angles down here. So that means that I'm going to have an apothem that is going to be 5 over 2 times the square root of 3, which is going to be 5 root 3 over 2. And I know my number of sides is 6. And then my side length is 5. So plugging that all into my formula, I have area is equal to 1/2 times 5 times 5 root 3 over 2 times 6. And that multiplies to 75 root 3 over 2 centimeters squared. If I had done 2.5 there, then I would have a weird decimal right next to my square root, and that's not like the most proper form of it, so it's better to keep our numbers as a fraction when we want to work with exact answers. Okay, example 4 is a little strange. It's hard to, I think, maybe it's not difficult, but it's interesting to think about a square as having this apothem inside of it, because the square is such a simple shape, and we know the area is just length times width. But we can also find area this way, and I kind of did it both ways so we could see that it really does give us the correct thing. So it said find the area of a square with an apothem of 4 inches. So I drew my center, and then I drew my 2 radii and my apothem, and then my apothem was 4. And because we're working in a square, I know I have 90-degree angles on the corners, which means that when my radius cuts that angle in half, it's going to give me 45-degree angles, which means I'm going to have 2 45, 45, 90 triangles. And because 45, 45, 90 triangles have congruent legs, then that means that this little piece down here is 4, and this little piece down here is 4. So we know that our whole side length is going to be 8. So if we were to plug that into our formula, 1/2 SAN, I would have 1/2 times my side is 8, times my apothem is 4, and then times my number of sides is 4, and that gives me to 64 inches squared. And then differently, because I was able to find that my side lengths were 8, I could have done length times width here and gotten that my area is 8 times 8, which is also 64 inches squared. Okay, for 4, it says find the area of an equilateral triangle with a radius of 12 centimeters. Exact answers only. This one's really strange because we're using a triangle inside of a triangle, but because it's only giving us our radius, we can't go straight from our radius to finding the height of our triangle. So it makes more sense here to construct this smaller triangle with an apothem and then use our polygon formula to actually solve this problem. So if I draw my central angle, I draw my center and I draw a radius here, then a radius here, and then I draw my apothem, and I know that my radius is going to be 12. So this length right here is 12. Then because I have an equilateral triangle, I know that the corners of my triangle are 60 degrees, which means these angles down here are going to be 30 degrees since our radius is always going to cut that angle in half, which means I have a 30, 60, 90 triangle with a scale factor of 6. So since my apothem is across from my 30 degrees, that means my apothem is going to have a length of 6. So plugging that into my area formula, I have area is equal to 1/2 times my side length, which is going to be 12 root 3, since my scale factor was 6, and going across from 60, I have a root 3 right here. So this little side length is 6 root 3, this is 12 root 3. So I have 1/2, 12 root 3, is my base, times the height of my apothem, which is 6, and then times the number of sides of a triangle, which is 3, and that gives me 108 root 3 centimeters squared. Now I could have, once I knew that this was 6 root 3, I could have found the height of my triangle by kind of drawing another altitude going from the very top of my vertex, knowing that this angle is 60 degrees and this is 30, and then this is 6 root 3. So that would mean that I have a scale factor of 6 root 3. So my height of my triangle would be 18. So then the area using base times height would be 12, 1/2, 12 root 3 times 18, which we can see is the same as this up here, since 6 times 3 is 18. So it does give us the same thing, and in this case it actually makes more sense to use the apothem since it's kind of constructed in that way. Okay, and then last one is example 5. We've got another hexagon. Now I have a hexagon whose side length is 20 root 5. So when I draw my 2 radii and my apothem, I can break my side length into 10 root 5 and 10 root 5, just cutting it in half. And then again, because we're working with a hexagon, we know the central angle is 60, so we know these two smaller angles are both 30, and we have 30, 60, 90 triangles. Then that means I'm going to have a scale factor of 10 root 5, so my apothem is going to be 10 root 5 times 3, which is 10 root 15. And then plugging that into my formula, area is equal to 1/2 times my side, which is 20 root 5, times my apothem, which is 10 root 15, times the number of sides is 6. And when I multiply all of these together, I multiply my numbers outside of my radical separately, and I multiply my numbers inside my radical separately together, and I get 600 times the square root of 75. But the square root of 75 is really 25 times 3. So I can take the square root of 25 and pull it out and get that this is 5 root 3. And then I'm just multiplying 5 times 600 to get me a final answer of 3,000 square root 3 centimeters squared. That's a pretty big hexagon. All right, and then lastly, what we're going to talk about is a little bit more complicated shapes. Now, example 6 is asking me to find the area of a decagon. And in general, I like to construct the whole shape because I'm a visual person and it helps me see it. But in the case of a decagon, there's so many sides, it's really hard to draw and have it be neat and really be able to not look like a circle. So in instances like this, I won't even draw the whole shape, and I'll only draw just the triangle that's created by my center and my 2 radii and then my apothem. So this is going to be kind of a zoomed in piece of our shape. So I'm going to have my center, and then I'm going to have a radius coming down and a radius coming down. And then this is going to be one side of my decagon, and then I'm going to drop my apothem. And then I'm just going to kind of go ahead and draw some other pieces so it looks like we're pulling this out of the shape, and we can kind of maybe visualize the decagon being much bigger. Okay, so my decagon has a side length of 4, so I guess I'll label that here so we can see that. Let me get a bigger marker. So because I have a side length of 4, that means my apothem is going to cut my side into lengths of 2 and 2. Now here what we'll have to do is we're going to have to find either our central angle or our angle down here. I'm going to find the central angle, but just a reminder, you can find this angle down here by using that other formula, n minus 2 times 180 divided by n. But I'm going to find the central angle in this instance just because it's a little bit easier of a formula. So I'm going to take 360 and I'm going to divide it by my number of sides, which is 10, which means I'm going to have a central angle here of 36 degrees. So that means this whole angle, kind of doing this again, this whole angle is 36 degrees, which means each one of these little angles is going to be 18 degrees. And well, right away we can probably see that we don't have a special right triangle, but we have an angle and we have a side and we have our missing side, which is our apothem, which I'll call x. So this is going to be a scenario where a trig function would be the best approach to this problem. So if I want to find what x is, I have to start at the angle that I know. And if I start at 18, then I can see that 2 is going to be opposite 18 and x is going to be adjacent to 18. This tells me I'm going to use a tangent function. So this is going to say the tangent of my angle, which is 18, is equal to opposite over adjacent, so 2 over x. And then solving for x, we would have that x is equal to 2 divided by the tangent of 18. And that's going to give us that x is about equal to 6.16. And I'm going to take this to 2 decimal places, even though it says round to the nearest tenth, because my final answer is going to be rounded. I want to keep some more decimals to start with, just so it gives me a more accurate answer towards the end. Okay, and then my area is going to be 1/2 times my base, or my length of my side, which is 4, times my height, which is my apothem, which is 6.16, times my number of sides, which is going to be 10. So that's going to give me approximately 123.2 inches squared. Now, just really quickly, if I were to have found this angle right here, the angle of my vertex, rather than this top angle, then I would have gotten that my vertex is 8 times 180 divided by 10. Which is 144. So that would be this whole angle is 144. So if I were to cut that in half, that would mean this angle down here is 72, and sure enough, that makes sense because 72 plus 18 is equal to 90. But if I were to use 72 instead, then when I set up my tangent problem, I would have had x is my opposite and 2 is my adjacent, and then I would have had tangent of 72 is equal to x over 2. So then x would be equal to 2 times the tangent of 72, which sure enough is equal to 6.16. So what's interesting about this is that if we choose the central angle, it's easier to find the central angle, but it's actually a little bit more challenging to solve for our apothem. And then if we choose to find our vertex, it's a little bit more challenging to find the angle of the vertex, but then it's a little bit easier of a trig function to solve. So they kind of balance out in terms of difficulty. So it's really about which one you prefer to choose, and either way will work. All right, so go ahead and go through this process and see if you can solve example 7, and then we'll go over that and then summarize the lesson. Alrighty, so I constructed my triangle with my 2 radii and my apothem, and I knew that one of my radius was 12, and then I found my central angle by doing 360 divided by 8, and that gave me a central angle of 45, and then using my apothem to bisect that central angle, that gave me 2 angles up here of 22.5. And then I used trig functions to find both the height of my apothem and the side length of my octagon, since I need both of those. So looking for the length of my side, or at least half of one of my sides, y, I was a sine function since y is opposite of 22.5 and h is my hypotenuse. So I did the sine of 22.5 equals y over 12, which gave me approximately 4.5922, and I always kind of take it 2 more decimal places than I want the answer to be, just so I have more accuracy. And then solving for my apothem, I got that since my apothem was adjacent to 22.5, I had to use cosine, so I did the cosine of 22.5 is x over 12, and I got that my apothem is around 11.0866. And then I made sure to double my y value, since that's just this length right here, and I want to find the side length of my whole octagon. And I got area is equal to 1/2 times my side, which is 9.1844, times my apothem, which is 11.0866, times 8, and I got that the area of my octagon was about 407.3 centimeters squared. Okay, and then I'm just going to leave you with just a real quick diagram of some really common shapes that we're going to see a lot and what our angles are in that shape. All right, so looking at our triangle, we know that the degrees inside of our triangle are 60, 60 and 60, and my central angle, sorry, I can't get my pen was frozen for a second. All right, so then my central angle would be 360 divided by 3, which is 120 degrees. So I've got a vertice of 60 and a central angle of 120. Looking at my square, I have vertices of 90 degrees. Sorry about that. And then my central angle in a square is going to be 360 divided by 4, which is also 90 degrees. Pretty interesting. And then looking at my pentagon, I have that one of my vertices is going to be 3 times 180 divided by 5, so that's going to be 108 degrees. And then my central angle in my pentagon is going to be 360 divided by 5, which is 72 degrees. And then lastly, I have my hexagon, and I know that one of my vertices is 120, and my central angle is going to be 60 degrees. So these are just ones that are going to come up a lot, and then we can use either our vertex or our central angle to construct our triangle that we're going to use to find our area. So these are just ones that are probably good to have memorized and just know, because we're going to see them so often, that they're good things to memorize. All right, that is it for 10.4, and I'll see you in the next one.